All right, so in this chapter, we're going to dive into system modeling. And really, what this is all about is creating the blueprints for our software. Before we even think about writing a single line of code, we need a plan. System modeling is that plan. It's how we make sure we understand what we're building so we can design complex systems that are actually robust, reliable, and do what the user needs them to do. So let's get into it and explore these essential software blueprints.
So I want you to picture this. An architect would never, ever start building a skyscraper without a detailed set of blueprints, right? Of course not. Those plans are absolutely critical because they let everyone, the engineers, the construction crew, everyone, see the building from different, essential perspectives. Now think about software. It's arguably one of the most complex things we build as humans, so doesn't it make sense that it needs the same kind of careful upfront planning? That's exactly what system models are. They are our software blueprints.
Okay, so what are we actually talking about when we say system modeling? Well, the formal definition is the process of developing abstract models of a system, where each model gives you a different perspective. And the two words to really latch onto there are abstract and perspective. The whole point isn't to create a perfect one-to-one copy of the final software. No way. Instead, we're creating simplified views. We're intentionally leaving out details so we can zoom in and focus on one specific part of the system at a time. And that's the magic right there. That abstraction is what makes something incredibly complex, well, manageable.
So here's how we're going to tackle this. We'll start with the big question. Why even bother modeling? Then, we'll look at the system from the outside in. First, its context and interactions, then its internal structure, and after that, its behavior. And to wrap it all up, we'll touch on something called model-driven engineering. All right, section 1, why model? Understanding the blueprint. So yeah, let's get right into that fundamental question. Why do we go through all this trouble? What's the point of making these abstract plans before we just jump in and start coding? Well, the main reason is pretty simple actually. Just one giant single blueprint can't possibly show everything you need to see. Think back to our architect. They have separate plans for the structure, the plumbing, the electrical, right? It's the exact same idea in software. We need different perspectives. So we need a model for the system's external context, where it lives. We need one for the interaction, how it talks to users and other systems. We also need a structural model, what it's made of. And finally, a behavioral model, how it actually acts when it's up and running.
This brings us to a really important idea, the difference between an abstraction and a representation. They sound similar, but they're not. An abstraction, which is what a model is a simplified view. It intentionally leaves stuff out to make it easier to understand. A great example? These slides. They're an abstraction of the whole book chapter. They just hit the highlights. Now, a representation tries to be complete. It's like translating the textbook from English to Italian. You're trying to keep every single piece of information. And it's so important to get this. Models are powerful because they simplify. That's their whole purpose.
Okay, let's move on to our second section, context and interaction, or the system in its world. We're going to start from the outside and work our way in, looking at how our system fits into its environment and talks to everything around it.
So, the first two questions we have to ask are really simple, but they are absolutely foundational. First, where does our system live? And second, who or what does it talk to? If you can't answer those two questions clearly, you're going to have a bad time. Getting this right from the start defines the entire scope of the project.
And that brings us to something called context models. Their whole job is to define the system's boundaries, to draw a line in the sand. They show us what's inside our system, the stuff we have to build, and what's outside, the things it just has to work with. And honestly, just drawing that boundary is one of the most important things you do early on. It stops that dreaded scope creep and makes it super clear who's responsible for what. Let's make this real with an example from the book, The MentCare System. It's for managing patient info in mental health clinics. Now, a context model for MentCare would show its neighborhood, so to speak. You can see right away this thing doesn't live in a bubble. It has to talk to a general patient record system, an appointment system, reporting systems, a prescription system, you name it. A diagram like this is gold for the development team. It instantly shows them all the other systems they have to connect to and what interfaces, what APIs they're going to need to build.
Okay, so we know who the system talks to. Now we need to figure out what they talk about, the conversations themselves. And for this, we have two main types of interaction models. And they're both part of what's called UML, the Unified Modeling Language. Think of UML as the standard grammar for software blueprints. So first up, we have use case diagrams. These show you what a user can do. They're all about the user's goals. Then we have sequence diagrams. These show you how the system actually does it. They dive deep into the step-by-step process.
Here's a simple example of a use case diagram. See the stick figure? That's our actor, in this case a medical receptionist. And those ovals, those are the use cases, basically the tasks they can do. Things like register patient, view patient info, transfer data. It gives you a really clear, high-level map of what the system needs to be able to do from the user's point of view. It's a perfect answer to the question, what can this person do with our system?
And now we go from the what to the how. This is a sequence diagram for that view patient info task. What it does is show the messages flying back and forth between different parts of the system. So you can see the receptionist kicks things off. The system then sends a message to the database. But wait, the database has to check with an authorization system first. Only if that's successful does the patient info flow all the way back to the user. See how this lays out the entire internal dance, the choreography, just to fulfill one simple request? This is so useful for developers to spot dependencies and things that could go wrong.
Okay, so that's the outside view covered. We've defined the boundaries and the interactions. Now let's peel back a layer and look inside. This is section 3, structural models, the static blueprint.
The big question we're asking here is what are the main building blocks of our system, and how do they all fit together? We're talking about the static structure here, kind of like the skeleton of the system before it's actually turned on and doing anything. And the main tool for this is the class diagram. Now, if you've done any object-oriented programming, you know what a class is. If not, just think of it as a blueprint for creating things, or objects. For example, you might have a patient class. That class would define all the things a patient has, like a name and a birthday, and all the things a patient can do, like schedule an appointment. A class diagram just shows us all these different blueprints and how they're connected to each other.
So this table here is basically a simplified version of what you'd see. You've got your classes like patient and patient record. The association is just the line connecting them. But the really key concept here is multiplicity. That just means the numbers in the relationship. A one-to-one relationship is easy. One patient has exactly one patient record. A one-to-many relationship means one patient can have, well, many consultations. This stuff is super important because it defines the basic rules of how your data is structured.
Of course, as systems get bigger, they get more complicated. So we need tricks to manage that complexity. One of the most powerful is called generalization. All it is a type of relationship. For instance, a consultant is a type of hospital doctor. A trainee doctor is also a type of hospital doctor. By setting up this hierarchy, the more specific types, the subclasses, can automatically inherit all the stuff that's common to all doctors from the main hospital doctor class. This is awesome because it means less repeated code and a system that's just way easier to understand.
All right, we've looked at the static blueprint, but software isn't a statue, right? It's alive, it's dynamic. So that brings us to section 4, behavioral models, the living system. We're now going to look at how the system actually behaves when it's running.
Generally, a system's behavior is kicked off by one of two things. It can be data-driven, meaning it springs into action when a bunch of data shows up that needs processing. A billing system that runs at the end of the month is a perfect example. Or it can be event-driven. This is where the system is mostly just sitting there waiting for something to happen, an event. Think about the user interface on your phone. It's just waiting for you to tap something. That tap is an event. For event-driven systems, the best tool we have is the state machine diagram. Let's use a super simple example, a microwave oven. A microwave can only be in one state at a time. It starts in the waiting state. You press a button, that's an event, and it transitions to a new state, like set time. You press start, another event, and it transitions to the operation state. When the timer hits 0, that's the final event, and it goes all the way back to waiting. It's a really clear way to map out every possible state and how you get from one to another.
And just like before, we need a way to handle complexity. That operation state in a microwave probably isn't just one thing. It might have little substates inside it, like checking the door is closed, turning on the magnetron, and finishing up. Instead of cluttering our main diagram, we can bundle all of those up into one superstate called operation. This lets us keep the main diagram clean and simple, but we can still zoom in to see the details if we need to.
Okay, this brings us to our last section, model-driven engineering, or from blueprint to building. This is a really forward-looking idea. What if our blueprints, our models, weren't just for humans to read? What if we could use them to automatically generate the actual code for the system?
So a really popular way to do this is called model-driven architecture, or MDA. It's a three-step process. First, you make a SIM, a computation-independent model. This is just the business logic, no computers involved. Then you turn that into a PIM, a platform-independent model. This is the really clever part. It describes the software in detail, but it's generic. It doesn't care if you're building it in Java, or for an iPhone, or for a web browser. Finally, you take that generic PIM and use tools to automatically transform it into one or more PSMs, platform-specific models. These are tailored to a specific technology, like Java, and you can generate the final code from them. The big win here? Portability. If a new technology comes out, you just create a new transformation from your PIM. You don't have to rewrite everything from scratch.
All right, let's wrap this up. What are the big takeaways? First, models are all about creating simple, abstract views to handle complexity. Second, we look at a system from 4 main angles: its context, its interactions, its structure, and its behavior. Third, we use a standard toolkit, UML, with things like use case and class diagrams to draw these models. And finally, all of this is pushing us towards a future of model-driven engineering, where our blueprints can actually help build the house.
And that leaves us with a pretty provocative question to chew on, connecting all the way back to our architect analogy at the beginning. As these modeling tools get smarter and better at generating code automatically, what does that mean for the job of a software engineer? Are we all going to become architects, designing these beautiful, high-level blueprints, and just let the machines handle the tedious work of actually writing the code? It's a really interesting thing to think about for the future of our field.